All right, let's get started. So last Friday we left off, we just had written down the equation for heat transfer through a composite plane wall. So we had the total temperature difference in the numerator and then the sum of all of the thermal resistances in the denominator. And I've been meaning to check in with you all. Is this still big enough for everyone to see in the back, or should it be a little larger? It's good? Okay, there's kind of a trade-off between how much I can fit on the screen and how big it is, so trying to hit the compromise there. Okay, so we'll write down, just very quickly, there's kind of another way of expressing this. So same equation, but another way you might see this written, and that is using the overall heat transfer coefficient, which is capital U. And were there any questions on this before we keep going? Okay. So U is defined as 1 over the total thermal resistance times the area. So if we look back at the way our equation is defined, we have Qx is the temperature difference between the two fluid temperatures, in this case, over the total thermal resistance. And then if we just multiply the top and the bottom by the area, this R total times area here starts to look like the overall heat transfer coefficient U. So then we can just rewrite this as, since U is 1 over R total times A, U is in the numerator here. So we can rewrite that as U times A times the temperature difference. So if you're given a problem with this overall heat transfer coefficient, it typically will mean that like some of the work has kind of already been done for you. So it's already been calculated for the R total through this different composite materials, and you can just plug it in to this equation. I'll write it down here so we can put a box around it. So now we have several different equivalent expressions for R total. So it's the sum of all the individual thermal resistances. As we showed on Friday, it's also equal to the temperature difference divided by the heat transfer rate. And now we can show that it's also equal to 1 over U times A. Okay, any questions before we move on to the same thing but for cylindrical systems? Yes?
Are we going to talk about how to derive like the circuit diagram from like a problem statement in depth anymore?
So how to, by derive it, do you mean how to figure out what the thermal resistance is, or just how to like write it down?
Just like a little bit of both, just like generally we kind of just like gloss over that.
Yeah, so do you mean specifically
like how we put the thermal resistances, like are there any other circuit elements, or is that useful in other contexts?
Yeah, so the circuit part of it is just kind of an analogy. Do you mean specifically how we showed like
Yep.
this circuit right here?
Yep.
Yeah, so I am going to do the same thing for the cylindrical system.
Okay.
And it's really more of a tool to kind of help you as you're going from looking at just kind of this setup where we have the different components and the different sections. And then you can write it down to where you have all of your thermal resistances just kind of laid out here. And then that's just kind of a step that helps you go from here to writing the equation. So then you have all the thermal resistances written out here, and then those just, the sum of those just gets put into the denominator. So I will show again, go through this for a radial system, and then we're going to go over the lab and recitation tomorrow, but I was going to have Abby do like 1 or 2 example problems, and one of which would be like a composite type of problem.
All right, that's what the plan. Thanks.
Okay. All right, cylindrical systems. So often, and that's what we'll do for this derivation, we treat heat transfer as one-dimensional in plane walls and also in cylindrical systems. So we'll say, for this case, we'll have heat transfer in the radial direction only. And this is typically justified by if you have, for example, a wire, a long, thin wire, the surface area of the wire is much larger than kind of the cross-sectional area. So you have heat transfer just going out in the radial direction toward the surface area rather than laterally along the wire. Okay. So we're gonna now talk about a hollow cylinder that has some hot fluid moving through it and some cold fluid moving over it. It is helpful to draw this out, but it's a little challenging. So I'm going to give it a try. So we've got the outer radius, the inner radius, and then kind of a perspective on it. Okay. There we go. And then, let's see. You can show we've kind of got a hollow center here. And then let's put a center line. Okay. So now flowing through the center, we have fluid, hot fluid that is at a temperature T infinity 1, has a heat transfer coefficient H1. And then flowing over, perpendicular to the cylinder, there's a cold fluid, which is temperature T infinity 2. H2 is the heat transfer coefficient. And then we're going to have some temperature at each of the surfaces. So the inner surface where the hot water is flowing through and the outer surface where the cold is flowing over. So at the inner surface, this is going to be TS1. And the outer surface here, TS2. And then we've got R1, the radius of the inner pipe, and R2, the outer radius. And then lastly, we've got a length, L. So the idea here is you have some hot fluid moving through. So even though you have the fluid in the middle and the fluid over the top of the cylinder moving in opposite directions, conduction is still occurring in the same direction within the cylinder, or heat transfer rather, convection and conduction. So heat transfer, heat is flowing from the hot fluid to the surface of the cylinder and out radially, and then out into the ambient air. And do note, we're using L here for the length. We also use L for the thickness of the plane wall. Just keep in mind that L isn't always the same thing problem to problem. It's just geometric distance. Okay, that's the general setup. So we want to do the same thing as before. We're going to kind of show the heat transfer with the overall heat transfer and the using the circuit analogy. But first, we're going to kind of go back to what we did last week and what we did in recitation. So remember, we did the derivation of the heat diffusion equation in cylindrical coordinates. And we've done a lot of example problems for applying that to Cartesian coordinate systems and applying boundary conditions and solving for the temperature distribution, taking the derivative, and then solving Fourier's law for the heat transfer rate. So now we're going to apply that to this problem. So we've got a cylindrical system. We're saying it's one-dimensional heat transfer. So we're going to first derive the temperature distribution using the heat diffusion equation. And we're going to, again, assume, like always, one-dimensional heat transfer in the radial direction this time, steady state, no energy generation, and isotropic. So under all those assumptions, you can reduce the heat diffusion equation in cylindrical coordinates to this first term equal to 0. And then if you integrate this once, and then divide the R through, and then if you integrate again, natural log shows up. So C1 natural log of R plus C2. So that's what the temperature distribution looks like. And it's interesting to note that if you remember, for a plane wall, this was always linear. So the temperature distribution through a wall just kind of looked like a straight line with a positive or negative slope. But through a radial system, it's logarithmic. The temperature distribution is logarithmic. So now we're going to say our boundary conditions. We set up in the problem to have constant surface boundary conditions. So TS1 on the inside, TS2 on the outside. This is kind of putting together a few different ideas that we've gone through. So the heat diffusion equation, solving it, applying the boundary conditions, drawing it all out for a composite system, and then writing that in terms of the total heat transfer using kind of the circuit analogy. So we're going through all those steps all at once for this problem. So we're saying constant surface temperature, let's see, T at the first radius, R1, is equal to TS1. And note it's not 0 this time because it's kind of the inner hollow cylinder. We're not at the middle of the cylinder. And the temperature at R2 is TS2. Constant surface temperatures, plural. So now I won't go through all the math, but you can, just like we did before, apply these boundary conditions separately, solve for C1 and then C2. And then you get out the temperature as a function of radius. TS1 minus TS2 over the natural log of R1 over R2 times natural log of R over R2. And note here, this R1 and R2, those are known values, right? They're the radius measurements that we know. And then R here is the variable R. Plus TS2. So this is the same process we've gone through multiple times for a plane wall. Same assumptions, same constant surface temperature boundary conditions. We're just doing it in cylindrical coordinates now. Okay. So once we have the temperature distribution, what is the typical next step?
Take the derivative for Fourier's law.
Yeah, so we want to find the heat transfer rate. That requires dt dx or dt dr in this case. So Fourier's law, and for cylindrical coordinates, in the r direction, looks the same for the r direction, but we have dt dr instead of dt dx. And then remember, the heat is being transferred through radially, so through the surface area. So the area now is expressed as 2 pi r, so pi d, so just the circumference, right, times the length of the cylinder. And that gives you the surface area. So K, A, and then our dt dr. And I know, so for Fourier's law, we only introduced it formally in Cartesian coordinates in lecture, and then in the recitation we went through the derivation in cylindrical coordinates. And I am writing up an equation sheet that has kind of the different forms of the equations. So we didn't formally introduce this in lecture, so I think that'll be helpful to just be able to look at a resource and say, okay, what's the right equation for this situation? Yeah. So make sure you have everything. That will make sure you have everything in one place. Okay. So now we need to figure out dt dr. So we're going to take the derivative of it. So we take the derivative and then plug it into Fourier's law, simplify everything out. Reduces to 2 pi lk ts1 minus ts2 all over natural log of R2 over R1. So again, temperature distribution, heat transfer rate. So now, we looked at Fourier's law to kind of derive the thermal resistance before, right, or to understand it intuitively, and we said kind of everything that isn't the temperature difference, if that goes up, then the heat transfer rate is going to go up, right? So if the inverse of it goes up, then the heat transfer rate is going to decrease. So the inverse of all of this out here is the thermal resistance, just like before for a Cartesian coordinate system. So for conduction, it's the natural log of R2 divided by R1 over 2 pi times the length times K. In cylindrical coordinates. So remember, we have convection boundary conditions for this problem, right? Or there's convection on the boundaries, but we took our boundary conditions to be constant surface temperature. We said we know the surface temperature at the inside and outside of the cylinder. So what we were doing when we derived the temperature distribution, if you go back to the derivation of the heat diffusion equation, that was just looking at conduction, heat transfer via conduction in and out of a differential element, right? So when we apply it here, we're saying, okay, it's the same thing. We know there's convection going on in the inner and outer surfaces, but we know the surface temperatures, so we can apply the heat diffusion equation and just calculate what the heat transfer rate is. But because it's this highly simplified case where we have, no energy generation, 1D, steady state, all of that, just like we did in homework when we did the double pane window, we know that the heat transfer rate through the system is going to be like completely equal through all the elements of it. So that's why you can say the heat transfer via convection is the same as the heat transfer via conduction. Does that kind of make sense? A little bit? Like tying a lot of the things we've been doing together. Okay. So the thermal resistance from convection is unchanged, except now you can express the area, so the surface area is 2 pi RL, and then times H. Okay. So let's try to write down the thermal circuit for this cylinder. So we'll go back to the drawing. And remember, this was just a way of kind of visualizing the temperature at each different kind of location radially or in the x direction, depending on your coordinate system, and then what the resistance is for the heat transfer between those two temperatures. So we'll start at the inner node, which is the first ambient fluid temperature, T infinity 1. And then we have some heat transfer going on, in this case, via convection. And so the thermal resistance for convection, 1 over HA, so 1 over H1 in this case, and then 2 pi RL, so 2 pi R1L. And then we come out and we hit this surface, which has a temperature of TS1. And then we go through the object, heat is transferred via conduction through the object, and we hit the outer surface, which has a temperature of TS2. And the thermal resistance for conduction in cylindrical coordinates, we just derived natural log of R2 over R1 over 2 pi KL. And then again, convection out to the outer temperature. So the ambient fluid on the outer surface is colder. It has a temperature of T infinity 2. And then again, convection, so the convection thermal resistance H2 2 pi R2L. This is hotter and this is colder. So we know we have heat transfer going from the left to the right, and that's Q sub R, heat transfer in the radial direction. Okay. So now, just like we did before with the plane wall, we can make it slightly more complicated, but we have all the tools we need to, write out the heat transfer rate still. So let's look at a composite cylinder. This would be way too complicated to draw, so I'm just going to draw kind of a cross section, just a partial cross section. So just like before, in here we have a fluid flowing through the cylinder. And out here we have another fluid flowing over the cylinder. So T infinity 1 and T infinity 4. And like with the plane wall, we now say these are sections A, B, and C. And the surfaces between each of these different sections are going to have distinct temperatures. TS1, T2, T3, and TS4. And then there's going to be kind of various radial measurements going out to each of the components. So that's going to be R1, 2, 3, and 4. And then let's see if we can just look at this and write down first the thermal circuit for it, and then the expression for the heat transfer rate. So I'm going to do that up here, but go ahead and try to do it on your own paper. Okay, so I had to expand out here a little bit just to fit it all in. But you can see if we step through T infinity to the first surface temperature, that's convection. So 1 over HA. So H1 is the convection coefficient for the first fluid, and then the area, 2 pi RL. Notice we're using R1, so the inner radius. And then for conduction, the natural log of the second radius divided by the first over 2 pi KL, and notice it's KA, so we can write that down too. We have KA, KB, and KC, so each section has its own thermal conductivity. And then the same thing for the other two solid sections for conduction. Here between T2 and T3, we use R3 and R2, KB, and then R4 and R3, KC, and then back to convection with R4. Okay. So now given that, if we want to write down the heat transfer rate, it's easier to be able to look at this thermal circuit and just say, okay, I just add up all these resistances, that's in my denominator, I've already got them written out, and then I just have the overall temperature difference on the top. So we'll write it out so you have it in your notes. And then just like before, we can show our heat transfer going this in the thermal circuit. Okay, so there's the overall equation.
And that's just a guess, right?
And that's what?
Just a guess, because we don't know if T4 or T infinity 4 or T infinity 1 are higher.
Yeah, so I was going with the same setup as the previous.
Regardless though, the sign will
Yes.
tell you which direction it's
Really?
Yeah, the sign will tell you which direction it's going. So this would be, I believe, if we had the origin at the middle and the radius going out like that, and then if we had hotter and colder, like set up before. Yeah. Yeah, but again, if you're confused with the sign convention, you can go back and write everything out with this equals this equals this equals this with all the negatives written correctly.
I know.
So maybe it would be helpful if we did a problem tomorrow where we have the temperatures like flipped from what we've been doing in the examples, just to show you that you can still work the problem even if it's not set up as exactly as it was in the example. And then, just like before, we have our overall heat transfer coefficient U. And that is U times A times the temperature difference. Yeah.
Earlier, at the beginning of lecture, you gave us an equation, R total equals the sum of the R's equals delta T over Q.
Mm-hmm.
And since I know this is kind of beating a dead horse, but since the signs are switched where that's actually negative delta T, I think it should be. Because this is T1 minus T4. And delta T usually means like the final minus thing.
I see your point.
Yeah.
It shouldn't really matter if you actually know like the direction of everything, but
You're referring to this equation?
yes,
Where is
I
it?
see it.
Here?
right there, yeah.
Yeah. So you're saying, yeah, I see what you're saying. You're saying that this should be negative delta T?
Yeah.
Yeah, okay.
I'm sorry I didn't bring it up.
No, I get your point. Yeah, so again, as long as your sign conventions and you keep it consistent, you should be good. But yeah, I get your point there. I'm not like 100% sure it's right, so I don't want to like completely confirm before I like look at it in more detail, but yeah.
Yeah.
Okay. So let's like take a step back and kind of think about what we've done. So we went through a lot of stuff. So basically we're just putting together, starting at a system that again is under these 4 assumptions that we've always made. And those 4 assumptions, one-dimensional heat transfer, steady state, no energy generation, and isotropic. That's what enables us to look at a system that is, you know, maybe it's just conduction through a wall, or it's conduction with convection on both sides, or convection on one side, or, you know, 3 different materials and convection on both sides. But those assumptions let us say that the heat transfer rate through all of those different layers of material or fluid or whatever is going to be constant. Okay, and that was what you proved in your first homework. Yeah.
And that's only for material in series, not parallel.
Right. So yeah. So you can also use this thermal resistance concept for materials in parallel. It's like a tiny little paragraph in the book, and I'm not going to cover it, but you can read it if you want to. Yeah.
How would you have materials in parallel? Like,
If you
cloth
had-
and a resin or something?
Yeah. So if you had like a wall, and then this was a material A, and then like this was B and C. See what I'm saying? No. So this is a wall, and then you have one type of material here and one type of material here. If you're asking like why you would have this, you just might. It's for a materials person to answer. Composites, I don't know.
What about a window and a wall?
But then it would be like parallel. A window,
That's
brilliant.
what I'm saying, is like,
You could think of a thermocouple because they use
Window.
the 2 different materials, and as they change temperature, you get different strains on them.
Derailed the class.
Yeah, sorry. So you could measure that here and figure out. Like,
Yeah, so this would be like heat transfer is now going from this section through both of these in parallel. Okay.
does that make 1 temperature on the outside or 2? Like, never mind. This is not.
You know, I bet the equation would tell you.
Yeah.
Yeah.
Not
It's,
bad.
yeah. So anyway, if you look at temperatures in parallel like that, you can do kind of an analogous thing where you have your resistances and you treat it just like you would in a circuit. Anyway, so we were talking about how you can have constant heat transfer rate through these different materials. If you've got convection, you've got a constant surface temperature, and then convection, whatever. And so you can use the heat diffusion equation to derive the temperature distribution within your solid, and then either you have constant surface temperature or convection on the boundaries. Either way, you know your boundary conditions, and you can apply those, calculate the particular solution for the temperature distribution, take the derivative, calculate the heat transfer rate using Fourier's law, and again, we're using Fourier's law, which is for conduction, But we know that that heat transfer rate is also going to be the rate via convection because we've said all these assumptions apply, and therefore the heat transfer rate is the same through all the materials, including via convection out into the fluids. So then we can write down this representation of the heat transfer through all these different sections via this kind of resistance concept. And then sum them all up in this total expression for the heat transfer through all of the sections. So again, like if you say this is just a single walled cylinder with just conduction going through it, this still applies, right? You just don't have any of these terms, and then this total temperature difference is just the delta T, and then you have your, 2 pi Ka, like 2 pi Ka would be on the top, and then your natural log of radius on the bottom. So it's just expanding that out into this kind of bigger expression for the heat transfer rate through all these different types of materials that have different characteristics, different thermal conductivities. And we can include convection in that because we know that the heat transfer rate is the same through all of the sections. Yeah.
Maybe you touched on this already, but the reason for not including the convection heat transfer rate in the first example.
Was it this one that you're talking about? Yeah? So we included convection on the inside and outside here.
The heat transfer rate equation that we derived did not have convection.
Oh, you're saying here.
Correct.
Yeah, okay. So this was just Fourier's law. So we're looking at the heat transfer rate for conduction only.
Yeah.
And then that was to develop, it's a good question though, that was to develop what the thermal resistance in cylindrical coordinates is. Yeah.
So that's QR, comma, con.
Yep.
Yeah.
Yep, good distinction. And then the thermal resistance via conduction follows from that in cylindrical coordinates. And then this is just the same as in Cartesian coordinates. But the area is defined differently. And if you notice here, this equation is still perfectly accurate because the temperature difference that we have here is the surface temperatures, right? TS1 and TS2. So we're just writing this equation for that one portion of the cylinder that is solid. And we could write out, is equal to Q convection equal to Q convection on the outside and the inside. And then that's kind of how we first derived this kind of big equation here. Setting them all equal to each other, then you can solve for the heat transfer rate, like we did in homework. Yeah, but yeah, good distinction, yeah. Okay, any more questions? Okay, so it's helpful to kind of have an overall picture of what we've done so far, thinking about it in terms of, so I guess for every setup we've had so far, just trying to draw the distinction between what we're doing now and what we're going to be doing next, which is going through kind of the same process for extended surfaces, so fins. And for all these systems that we've looked at, we have, even though we have fluid moving through the cylinder and across the cylinder, we're still assuming that we just have heat transfer in one direction, in the radial direction. And that heat transfer is the same direction for convection and conduction. And like in the plane wall, it was just in the x direction, even though you had conduction on both sides. And for fins, for extended surfaces, kind of the big distinction that you need to think about, and we'll write this down in the notes too, is now you have a very thin surface and you've got conduction in one direction and convection perpendicular to it. So that's kind of a big distinction that I want you to be thinking about when you're kind of looking at the systems that we have been looking at before, just like cylinder or plane wall, and then fins, extended surfaces. So you have to treat them a little bit differently, come up with different equations, and kind of redo the math for those particular setups. So I always end up with like 5 minutes. I'm like, I don't know if I should start a new topic. I'll go ahead and write it down. If we wasted 5 minutes every lecture, it would be like a whole lecture, right? So let's talk about extended surfaces. Okay, any more questions on what we just did? And I'll do a couple of, or I'll have Abby do a couple of 1 or 2 example problems with kind of the composite cylinder, and maybe like flip the temperatures around or the x direction around, just to show how to work those problems tomorrow. And so this is going to be some of the material for your first lab. Okay, so fins are thin geometries that protrude into the surrounding fluid. And you probably know the point of fins is to enhance the heat transfer, and that is via convection. And if we look at our convection equation, HA delta T, if we want to increase convection, we can either increase the coefficient, increase the area, or increase the temperature difference. Increasing the coefficient typically involves increasing the ambient flow speed, and increasing the delta T typically involves cooling the ambient air, both of which are fairly expensive. So the last option for increasing heat transfer via convection is by increasing the surface area, and that is the purpose of fins. So fins increase the surface area. Okay, we'll leave it there and then start back up deriving our heat diffusion equation for fins on Wednesday.